presentation, we will now not have a communication sensing, but only the sensing. It's about silent speech. So the idea that we can use mmWave radar to detect a lip or mouth movement for detection of speech. Okay, the speaker is Shang.
Hello? Can you hear me? Yeah. Hello, I'm Shang Zeng from Nanjing University, and today I'm here to present my work, mSilent, for general purpose silent speech recognition using commercial mmWave radar. And for the silent speech recognition means recognize silent speech by the articulatory gestures like the lip moving that allow the user to speak without making a sound. So that in some scenarios, like the library or conference room, that is important. And also some researchers try to use a wireless signals-based approach compared with the video-based approach that is compatible with mask and dark scenarios and has less privacy concerns. That is important in bedroom or night driving. That looks good, but the previous system only work in very limited corpus, that is less than 100 simple deterministic commands. That's more like the gesture recognition than speech recognition, and limited application scope to a simple interaction with the assistant. So why? The first reason is the limited resolution of their wireless signals. And the more important one is the insufficient capability of their recognition models. So our solution is to use a commercial mmWave radar with a normal model, combine signal processing with deep learning. Our work can work in large than 1,000 general conversation sentence, and as you can see, the user in the public speaks can input their delivery address to our system. That's a complex input, and and we enable some new application scenarios. The first is a more complex interaction with the voice assistant, and on top of that, we enable the more general applications in daily life, such as communication and input. And for our system, we collect the silent speech in the general corpus at larger than 1 meter. And first part is the signal processing pipeline, and then the feature was fed into an end-to-end DNN to translate it to the silent speech text. The first part of our system is the algorithm to separate the articulatory gestures from the multi-path reflections. There are so many movements, like we hand moving, like yours movement. The challenge is that the lip moving is both weak and complex. As you can see, when typing the keyboard, the speaking movement cannot be seen in this figure. So our solution is first, the whole body can be easily detected, so we use a cluster algorithm to form each body, and then, as you can see, our mouse, the articulatory gestures must appear at the top of the body, so we can directly select the zone by the location pair. And then we form a multi-scale detrended spectrogram. The first is to detrend. Why detrend? Because our head is moving when we speaking. It is unconscious. So our solution is based that the head movement is slowly varying, but the articulatory gestures is fast changing. So we use segmented linear detrending to remove that. And then, because of the duration of the articulatory gestures is varied widely from 100 to 700, so we perform STFT at multiple scales, 1 bias time and 1 bias frequency to extract the features for our articulatory gestures. And then for the DNN design, the first part is front end. We use the TF convolution as the base and as the base of our design, and we use the frequency downsampling to aggregate the features. And final, because of the MSDS is multi-scale, has multiple shape, we use fusing them by the element-wise addition. And for the backend, because both the input and output are long sequences, we use the transformer and sequence-to-sequence structure. And finally, we use user adaptive learning, and that also named transfer learning for new users. And for our dataset, to make our dataset fully general, we automatically collect over 100,000 transcripts from multiple websites and randomly select 1,000 sentences to form the corpus. As you can see, there are some examples. They are all fully general sentences. And for the data collection, we use both video and the millimeter wave radar, that is both for comparison and for our future work to fill the multimodal data. And for the experiment results, we can achieve less than 10% average WER in our general corpus. That is comparable with the state-of-the-art video-based systems. And also we have a big improvement with the previous systems designed for their limited corpus. That is why we design our system. And also we work well in challenge scenarios. The first is the new room, because we are robust across environment and sessions. And for the noisy, we use the noisy conference room and driving scenarios to prove our robust for irrelevant movement. And then, as you can see, when user is wearing mask, we can also work. And we conduct 2 case studies. The first is in-car assistant. The user, the driver, can talk with our assistant mSilent while the passengers are speaking or sleeping or others. The driver can set the destination, request for weather or not, any other input with the assistant. And the second is text entry interface. The user can perform speech input while in some scenarios that the traditional speech recognition is improper, such as the museum, conference room, band rooms. And we both test the WER and the word per minute. That is both good. And to conclude, to the best of our knowledge, mSilent is the first general purpose silent speech recognition system based on wireless signals. And we also make the following contributions. The first, we present the first signal processing pipeline to extract articulatory gestures from our millimeter wave signals. And then we design a novel end-to-end deep neural network to recognize silent speech in our general corpus. And finally, we evaluate mSilent in some of general conversation corpus that is larger than 1,000 sentences. Okay. Thank you. Any questions?
Do we have any questions? Because then we can actually also take the questions to the panel. So we have now the situation, there's still one presentation on the program, but I was just informed that the last presenter was not aware that the presentation is actually here presented. So we don't have the last presentation. We will just now have the panel. So I would like to invite all presenters to the stage. And we will talk about, so basically we span a number of topics right now. So we started with ultra-wideband, then we had a Wi-Fi based system. There was millimeter wave then. We also talked about the point cloud, and communication sensing was covered. So a wide range of topics. One topic we didn't cover was with the